Hi everyone, my name is Mariam Safi and I am pleased to welcome you to the AES Germany Research Colloquium with the topic of From mp3 to Party. This colloquium will be held in English with a talk by Professor Dr. Engineer Karl-Heinz Brandenburg introducing the topic, followed by a Q&A session. On our website, you can find more information about research colloquium events or any other local events around you by subscribing our newsletter. You can find the QR codes here as you see. This event is organized by the AES Germany section. And on behalf of the team, I would like to thank you for your participation. I would also like use this chance to thank Sue Williams for her support over the years, especially in organizing the research colloquium for us. So many thanks, Sue, even if you are probably not here today. So I think this is the time that I would invite my good friend Bartek to introduce our speaker for today and also to moderate the Q&A session. So Bartek, the microphone is yours.
Thank you, Mariam. Hello, everyone. My name is Bartłomiej Chojnacki. I'm the assistant professor in the AGH University of Science and Technology in Krakow, in Poland. And by the invitation of the AES Germany, I have a pleasure to chair today's meeting and to introduce our today speaker, who is Professor Karl-Heinz Brandenburg, the CEO of Brandenburg Labs and senior professor at the Institute of Media Technology and Technical University in Illmenau. Karl-Heinz Brandenburg received the degrees in electrical engineering and mathematics from FAU Friedrich Alexander University in Germany, and then the PhD degree in electrical engineering from the same university. He is currently a senior professor at the TU Illmenau and CEO of Brandenburg Labs, a startup company specializing in immersive audio technologies. Following times as a postdoctoral member of technical staff at AT&T Bell Laboratories in Murray Hill, USA, and again in FAU, he joined the Fraunhofer IIS as a head of the audio and multimedia department. He is the founding director of the Fraunhofer IDMT in Illmenau, where he retired in 2019. For his pioneering work in digital audio coding, he received many awards as a main contributor to the mp3 and AAC audio coding standards, perceptual measurements techniques, wavefield synthesis, psychoacoustics, and analysis of the audio and video signals. I'm very pleased to give the microphone to you, Karl-Heinz, and please follow up with your presentation.
Okay, thank you very much. Good evening, good afternoon, good morning to people who come in from far away. And hello to my talk, which is titled From mp3 to Party, How Signal Processing, Psychoacoustics, and Machine Learning Fit Together. In fact, it's not the first time I use this title. So for some of you, it might sound familiar. But I have both old and new content in there. So I will start with the usual introduction of once upon a time, listening tests, starting with Edison and a short history of audio coding. And then I'll talk a bit more about what we learned in hearing and some of the newer topics. So this is music information retrieval, which has been around now for 25 years as well, and especially spatial audio, how we call it these days. In fact, for listening via headphones, there's the biggest progress been in the last couple of years, and I will talk about what has been tried, what are we doing today, how to judge the quality of these systems, and then talk about some more science fiction-like ideas, what we want to do in the future. But let me start with a very early version. Once upon a time, Thomas Alva Edison not only invented the phonograph, but tried to make a big business from this. And to show people how well that works, he sent out people around the world to showcase his technology and especially the fidelity, the audio quality of these systems. So they did, in fact, what we today would call blind testing. Big auditorium, a phonograph or diamond disc later on, and then some live musician with a cello or singer or so. The lights were dimmed and the question was, what do people hear? The actual musician or the phonograph? And we are told that people said they couldn't distinguish. So from today, it sounds a bit odd that people couldn't hear the difference. So what happened? One thing is that the special artifacts from that time were not known, so new that people just didn't listen to them. They thought, okay, this is voice, or this is a cello, and this is a cello. There are other possible reasons apart from this, like people were old and couldn't hear. I don't believe that. Probably there were many young people there as well. Then what else could be there is that people did react to the new and just found it great without saying they could distinguish. And what we are told, the cellist trained a lot, practiced a lot to make his cello sound like the phonograph. Okay, so that's blind testing. Fast forward, audio signal processing, audio coding, success story over now many years. Today, this is done. This is everywhere. More than 65% of all music is sold via non-physical distribution. We got mp3 decoders everywhere. And estimate is that there are clearly more than 10 billion devices deployed who understand that technology. But how did it start 40 years ago? At that time, there was coding of pictures, of video, of speech. But for high quality audio signal, the standard textbooks of that time told us this can't be done. People will always detect the difference. And at several places in parallel, people tried to do what seemed impossible at the time. So this was the start of work at Erlangen, at Duisburg, at Murray Hill, at Hanover, at Munich, at Tokyo, and some few other places around the world at the same time. So yes, it did work in the end. In fact, I got in because my thesis advisor thought this could be done and was looking for a PhD candidate who could prove that this is possible. I thought, no, I think it's not possible, but let's try. Of course, as you all know, the basics there are psychoacoustics, like the mask threshold. If we have here the loudness and we have frequencies up to 20 kilohertz, we have what we call hearing acuity, basic threshold of hearing, which is different from person to person. But if we have some signal, like narrowband noise at 250 hertz, 1 kilohertz, or 4 kilohertz, the actual curve is bended. We have masking towards lower and especially towards higher frequencies. And what we do in the traditional way of audio compression is very simple. This is a picture from the MPEG-1 standard. We just try to do the same what happens in the ear. In fact, these masking effects happen in the ears. That's mechanics of how the hair cells are moving on the cochlea. And we do something similar by having a filter bank. We're trying to estimate from the formulas we know from psychoacoustics how much noise could be audible for a block of signal, short time block at this time, and then we can get a loud noise, what could be there. And then it's very simple. We have quantization done, and then quantization error is modeled as being a noise. This is really, if you can add or subtract anyway, we get a noise by quantization, and we are trying to modify the quantization. So for every frequency at this point in time, we get no audible noise. And then we have to do bitstream formatting and everything is done. So that's it basically, and that's the basic idea, which was so successful over the years. But this is not everything. In fact, that's a slide proposed by my good friend James D. Johnston, JJ. And what this slide points to is one very important effect. This is not just going from the ear to the parts of the brain where we detect auditory objects, but there is a feedback loop as well. From what we hear, we get loudness integration, which is still more mechanical. We get a feature analysis, so we can hear what sounds there are, which loudness, which tones, and so on. And here we can, in the end, recognize instruments, voices, and all that. And from that, there's a feedback loop even to the ear. So this is not a simple scheme, but very complicated by virtue of this feedback. And we have to be careful of thinking about this feedback and about the effects which happen in cognition. In fact, I will say that a couple of times more. Basically, what we hear is based on expectation. So as one example, people from Huddersfield University, some master thesis student showed the result of a study they did analog hearts, digital minds, an investigation into perception of audio quality of vinyl. So they wanted to find out what sounds better for people, vinyl or CD. And for that, they had a vinyl disc. They told everybody, oh, and by chance, we did the same recording then directly to a digital audio workstation as well. So we have the very high quality vinyl and the digital audio workstation, and we'll switch back and forth, and they ask people what sounds better. And with statistical significance, 60% of the listeners said they preferred vinyl. What they did not know was that, in fact, it was the same signal, because this disc, you can see that it's very regular. This contains just a time code to play back the signal from the same digital workstation. So we know our brain, our ears, what we hear, it can be fooled, and that's very important to know. In fact, what we need to learn as well is that the signal processing in our ear and brain is not just linear and time invariant. So from preceding experiments and other basics of psychoacoustics, we know it's not linear. So we can't use standard linear optimization theory. In electrical engineering, we all learn these nice ways to optimize to get optimum results. No, if we optimize for signal to noise ratio, in some cases, and especially in audio coding, we get worse artifacts. It sounds worse, not better, if we have within the same system a higher signal to noise ratio. And in fact, it's not time invariant either. We have what we sometimes call training effects, things happening in our brain, really changing the way our brain works over time. And this has been noted both in audio coding and in spatial audio rendering. And what the interesting fact is, we'll talk about that later a little bit again, it's not the same way for listening to artifacts. We know training helps us to detect finer differences until we reach a certain glass ceiling. And then we are at the physical limits of our ears and we can't hear more of the artifacts. But in spatial audio, people can learn to listen with other people's ears. They can learn that they want to have the illusion of immersion and so on. So people can learn to experience better externalization, better spatial audio. So that's the other way around. If we do too much training, it doesn't help us. We think it's great, but if we take somebody who hasn't listened to this before, it's not that great. So let me do a fast forward from what's been known from basically the 80s to current topics in audio signal processing. Even some of that is still relatively old, like music information retrieval. There's still a lot of progress, the question of how to recognize tunes, how to even do a complete transcription from polyphonic music to the actual score. That is still an open question, but there are very good results now. Then plausible audio rendering via headphones has been an old topic. I'll talk most of the talk about this. And then in the end, I'll go for personalized auditory reality, this party system, which we hope to have at some point in the future. These are topics we are working on in Illmenau, so internationally there's much more. Just one example for the music information retrieval. Again, already 20 years ago, we had some research on recognizing tunes. And people who hum or sing a melody should be recognized what melody this is. And it worked quite well. We wanted to find out how well it works. So we put a system into one electronic superstore in Munich 18 years ago. We called it Top 100 Suchmaschine because you could search for one of 100 melodies and people had the task to sing or hum into the machine. And we did anonymous recording and we found something we didn't expect. Afterwards, we are always smarter, of course, and say, of course. But from what we recorded for clearly more than half of the people, more like 70 or 80%, neither the machine nor any human had the chance to recognize the tunes. People were just not able to sing in a way that it could be recognized. So this was used for other purposes a bit, but it was not a big success because it's more like a toy again. Now let's go to immersive sound. Now back. I don't know how many Star Trek fans we have here around, but you might know the holodeck, which has 3D. You get immersed into some situation with all senses, and it's interactive. In video, there's a lot of work in that direction, but how to do that for audio? So people have tried for many years to do this with loudspeakers, starting with surround sound, which works only in the sweet spot in the middle. Then there have been techniques derived from the same mathematics background, wavefield synthesis and ambisonics. I'll talk a little bit more on this. And there's other technologies like vector-based amplitude panning, VBAP, and combinations like MPEG-H, which is now in use in quite a lot of broadcasting systems together with very high resolution TV. So just that you see one formula. This is the first and last for this talk. The so-called Kirchhoff-Helmholtz integral, which gives you both the basic idea of wavefield synthesis, but at the same time, the mathematics behind ambisonics. All can be derived from these basic equations. And this just tells you if you know everything from around a surface, then you can deduct everything which happens in the inside. And that's basically it. So from loudspeakers, we can use this technology and we got very good results. Great demos now for more than 20 years. And there's some of this even in commercial use nowadays, not just in big venues, but in cinemas with some reduced possibilities, but it's there. But if you want to have the same impression of being somewhere else acoustically, if you use headphones, usually the sound comes from within the head. We can get front-back confusion and so on. It does not feel real. So what's happening? People have tried that for basically 50 years. And the work started with dummy head recording. You might remember there were even radio plays in the night over the usual stereo FM systems with dummy head recordings, which gave you some great effects. So you could hear somebody whisper into your ears. So this did retain the time and phase relationship. It included some head-related transfer function. It gives you some great effects, but it's not good enough. It doesn't work for everything and everywhere. So the head-related transfer functions are, of course, very important in this context. If sound comes to our ears from different directions, but you all know that, you get filtering. And depending on direction and frequencies, there are large differences, not just small ones. So people thought, okay, since the heads of people are different, especially the ears are different, let's measure these and do individual HRTFs per listener. This does help, but it's not good enough. Another try was at the same time. That is okay. Of course, one HRTF would not make it. That's one direction. And if we turn our head, in reality, the sound is changing. So it should change here as well. So people did use head tracking, first only with rotation of the head, and adapted the HRTFs in real time from that. That gave sometimes great demos. I remember some of these from, again, more than 20 years ago. But it still left something open. Sometimes it worked great, sometimes not so great. What's happening? Okay, something which we should know is we need to use room simulation on the signal. We need to take in the influence of the room. So people did that. Then people did systems, like even some commercial systems, use all of the above with training. That's currently the best commercial system, but still not good for all applications. So we started thinking, and others as well, what's wrong? What have we not seen? And what turned out is that we had not got the effect, which is very important, that our brain remembers not just sounds like speech and musical instruments, but the environment, the acoustic environment. And that it always takes what we listen as compared to what it has heard before. So I remember at the AES Headphones Conference in 2019, Dr. Hammerschoy in one discussion said, when listening to sounds, our brain is a great pattern recognizer. It continually compares what it hears with what it expects from memory. These expectations are important, and there are a number of different little experiments which prove that, like the McGurk effect. You see somebody speak, you hear somebody speak, just syllables. If this has been synchronized, but it's not the same syllables which are shown and heard, then the brain gets confused and hears another syllable. That's the McGurk effect. Or what we've then proved already 10 years or more than 10 years ago in Illmenau in PhD work, so-called room divergence or room convergence ideas. And that's an old anecdotal evidence. If we listen to some spatial sound in a room, there's one condition where it works much better than in other conditions, and that's if we are in the same room for recording and playback. In fact, I remember being a child that I heard this effect from a stereo microphone set up with a tape recorder, but in my room at home, and I was frightening, was so plausible, so good. So we need to get that effect back, and that's what a lot of the new work in Illmenau is. So the usage of the acoustics properties of the actual listening room, very important. This is a PhD thesis by Stefan Werner. Then there will be one more slide on adaptation and training, PhD thesis by Florian Klein. There are other publications which show that there are both short-term and long effects. Sometimes we remember rooms and their acoustic properties after many months already. And then it's not just the head turning, but if we walk around continuously, the sound changes a bit, the sound which reaches the ear drums. So if we can do 6 degrees of freedom tracking and move around in the reproduction area, then again, we get much better spatialization, much better plausibility of sounds, much better externalization. So once again, for the time varying effects, there's short time and long-term effects. The adaptation to a new room, like what's the direct to reverberant ratio, which corresponds to distance, that can be very fast. And again, we can recognize and remember for quantized time. In fact, if we are in virtual rooms, we don't have the exact comparison. So in the beginning, externalization increases. Some people can get quite good immersion in virtual acoustics, even with current head-mounted displays and so on. But understanding the scene is very important as well. Making sense of the information, like in an exploration process. If I walk towards a virtual loudspeakers and everything is correct, then I get a really good plausibility of this reproduction, and I can even judge with some accuracy distance. Still, we know distance to make out the distance is much more difficult than just the direction of something. Familiarity with the content is very important, and that's why I'm always a bit nervous when people do these tests with just some type of noise, because really the familiarity, the recognizing is important. Again, illusion of moving through a virtual scene. If we do that via tracked self-movement, it enhances immersion, and that really supports the auditory illusion to a big degree. The rotation already helps us to reduce front-back confusion, and it supports externalization. And again, position tracking allows better understanding of the scene. If I walk nearer to some sound source, I can get even the near distance effects and so on. So that is much better in terms of distance perception and so on. If I just stay at the same point, I don't know, okay, I have a certain loudness, but what's the reference? I don't know. So for all of this, we have built a system at Brandenburg Labs, built on the research at TU Illmenau and other places like Aalto University and Technische Hochschule in Köln. And we don't have a real name yet. We just call it C3K. That's an internal nickname. And the idea is to use everything we need in terms of cues, which are necessary to get very good plausibility, but still have a relatively simple system. And for that, we compare real loudspeakers and virtual loudspeakers. We can switch back and forth. So what we do to do this rendering, we measure room impulse responses from real loudspeakers to a reference point. Traditional method with sine sweep. Of course, in the future, we would love to have better methods to extract room impulse responses from the environment. Then we need 6 degrees of freedom fast tracking. People have tried to turn their head fast to find out whether it's virtual or the real sound sources. And if we do fast tracking like we can do currently with HTC Vive trackers connected to our rendering software, we can then do real-time extrapolation of binaural room impulse responses according to the actual listener position. So we walk around and this is done in real time. No predefined points, but really in real time. And something which is probably a bit surprising to some people who worked a long time on the importance of head-related transfer functions, we just use standard dummy head HRTFs from, for example, a Keymer or KU100. These are available publicly, and that's enough for our demo. So I'm now taking slides I got from Ulrike Slummer from her presentation at the last DAGA. And this shows how we, and in fact, how Ulrike and the people working with her found a way to do an actual test where you could compare real sound sources with virtual sound sources in a room. And for that, we did a LiDAR scan of the room. This is how it looks then if you watch the room through the head-mounted display. And then you hear something and you have to use the controls of the head-mounted display to say, where do you think that the actual sound source is? And you can see here a little bit into getting what we call Raumschaukasten, where we see all the sound sources and where the listener is. Here, that was a microphone originally going that direction. We got 25 participants. We did 3 repetitions. We had people from young to old, but mostly I think the average was probably more like 27, 28. And we had a setup of the room, which was like this one. We had here the microphone position that was the reference for measuring the room impulse responses. We had 5 loudspeakers, 1, 2, 3 pointing directly to the listener, 1 pointing to the window, 1 pointing to the outside wall. And we had 3 conditions. One was we had the loudspeakers actually in the room. Of course, that means you can't really do 6 degrees of freedom, because if you walk around and don't see these, you might bang your head against the loudspeaker. That's not what we wanted to have. So people had to be at this place for listening, which makes it a bit more difficult. So we had the real speakers, we had a spectral decomposition microphone array, as you can see it here, and we have our C3K algorithm. So this is a fully blind comparison. Unfortunately, just 3 degrees of freedom. What we found and what's known from literature, that humans are not that good to find the actual distance from a source if they don't see it. And for some of the conditions, like pointing to the wall, we got quite some difference in the angle recorded. So we know that localization is known to be difficult without visual cues. But doing some statistical analysis, we got similar plausibility ratings across all 3 oralization methods. So both the oralization methods with virtual sound reproduction were actually so good that people could not reliably distinguish them. So the results indicate that our binaural algorithm is feasible for usage in most real-life applications. I'm always cautious in how to frame this. We had, in fact, a lot of anecdotal evidence, and I know a number of the people listening here have been part of one of these demos. We now have at AES conferences and other exhibitions, mostly people from the audio world, starting with Tonmeistertagung 1.5 years ago. We have now more than 700 listeners. We just did a check. Does it work for you? Is it really externalized? We did not do as accurate distinction like in this test, but this is anecdotal evidence from more than 700 listeners. And I call that a scientific proof as well that it works. Anyway, this is how the results look like if we put everything in here. We got both experienced and not so experienced listeners. We got some participants which had so many differences in their ways they judged this, that they clearly didn't understand the task. We had repetitions of each condition, so we know that. We have 45 trials and 15 different conditions, like the 3 different methods and the 5 different loudspeakers. And yeah, let's go into more details. Here you see the different positions. Straight on is the best in terms of direction. This is still very good. Here we get a lot of confusion about the direction for all the systems. That was pointing to the window at the side. Now, let's again look at this and then the reference. So here people were listening to the real sources. And we see even for the real source, this is where people are listening, and that's the different ideas about the distance, and there's clear a lot of difference. And then here, distance and angle are different. Yeah, same here. So that's the real source. That's the spectral decomposition method. Very similar in results again. That's C3K. That's the Brandenburg Labs algorithm, which is hampered because it usually needs 6 degrees of freedom to get really plausible reproduction. But still, people did get sensible answers for that in a lot of cases. And then this is a reference again, just to compare. So again, to get to some basic results of all of that, we need all spatial audio reproduction to think of where we are, the context of use. And they are really context-depending quality parameters, and we know that auditory visual divergence makes a difference. In fact, it's not a make or break difference, but it helps quite a bit. And especially if we talk about getting a sense of distance, yes, that's really what is very important. And then we have the room divergence effect. So if we play back the sound in an environment where the acoustics are very different, or even a little bit, we don't know the limits yet. We are just trying to find these limits, but we don't know them. If it's different, the brain says something is wrong, and the whole plausible reproduction breaks down into the usual in-head location or just around the head and so on. So that's why we, in the moment, have very different systems. There's a lot of people trying that, but usually you get, for a certain time, for a certain situation, very good externalization, but then again, the sound is near your head. If you listen to our demo, the effect is if you stand still, you don't get some of the cues the brain needs. The sound might be near your head as well. I've experienced that myself. And then I start walking, for example, towards the loudspeakers, and then the sound jumps outwards, and we get very good, very plausible reproduction. So to summarize these, we need a match between our expectation of a given sound in a given environment. So really, that the sound in an environment must meet the expectations, what we remember. And in fact, this works whether we see something or not. So it helps to have more open headphones to listen to that, because then you get the real environment in addition, and you can, it's easier to find, no, this really matches. And then there's a number of factors. And all sentence here, and you can read it in most publications until now, that cues for our own anatomy, our own HRTFs are important. Now, if I talked about these 700 listeners, or if I talked about everybody in this test, there was no individualized HRTF. We used just some mean values. So I know a lot of companies, including Meta and Microsoft, a lot of researchers spend a lot of work to find out more about HRTFs and how to optimize them and how to measure them with some photos or scanning and so on. My bad news for them is, sorry, you try to optimize on the wrong side of things. It can work without that. We need cues for the room, like reflection patterns and so on. And what we need there is still an open question. There are a lot of people who try just to use some information about the about geometry of the room and about the reflectivity of the walls. I have listened to some of these demos. I think it's not there. It can work somehow, but it's not really working fully. Of course, visual cues help. Proprioception helps, the feeling for our own body. And one major factor, which of course helps us to get to nice immersive feeling over time, is our own experience. If we listen to such systems long enough, the requirements get less. We still can get very nice reproduction. So how do we evaluate these systems? Can we do perceptual evaluation of spatial auditory illusions? And for that, very important words are authenticity and plausibility. Authenticity is if I have an external reference, like in the old days with audio coding, we switched back and forth between the real thing and the coded and reconstructed, and there should be no difference, nothing audible, which is, depending on the scene, really difficult to have for spatial audio. So the other idea is plausibility, agreement with an internal reference. Usually this internal reference is remembering a real version. So that's what we do with our demo, that we have the real loudspeakers there and we tell people to listen to them and establish an internal reference. Of course, even that doesn't work if we have fictive content, so no real version available, like ghosts, fairies, speaking animals and all that, or virtual reality scenes like what they want to do in mp3. Speaking a little bit more on the quality parameters, my favorite one here is externalization. While we usually do that on a scale from 0 to 100 or 0 to 1, for me, it's a 1 or 0 decision. It's there or not. If I hear something near my head, even if it turns the right way, if I turn my head, I call it no externalization. If I hear something from 3 meters distance, yes, it works. Then, of course, there's localization accuracy, but as we learned again, and we know for a long time, even humans are not that good. For such a system, we have to take care that it has high generic sound quality. So no coloration, no clicks, no audible changes in the image, the audio image when we move. All these things should be absent. This is easier said than done. Earlier versions of our demos had quite some of these. And to have the exact correct amplitude is still something not so easy. So with earlier versions and other systems, known ways to trick the renderer is to do very fast head movement. So then you see, oh, but the sound follows the head movement with some difference. That must be the virtual version, not the real one. So with fast tracking, this works. In fact, the numbers here from some publications should be faster than 50 milliseconds from the movement of the head to tracking, going to the rendering algorithm and going back to the eardrums. Our current demo does less than 20 milliseconds. And then people often ask, what about hate or near field effects? It's work, but there are very easy versions how to do that. One is near field effects. In our demo, we use standard loudspeakers with known characteristics. So these are in the rendering algorithm, so you can get very near to the loudspeaker and it still works. With hate, it's as simple as well. The algorithm works in all three dimensions. Of course, the measurement of the room impulse responses is only from one sound source to the microphone. But we do include the basic geometry, including distance to ceiling and floor. And with that, the algorithm does take care of hate effects. We have seen a lot of people who kneel down before the real loudspeakers to find out what the virtual reproduction does that in the right way. And we can say, yes, it works. Great. So for all that, we are looking for commercial use in the future. Of course, we see what Apple and others try in the moment. We think we can do it better, both in research and what we think can be future products. Recording studios can check the quality of their multi-channel mixes. In fact, we have heard from the Emil Berliner studios in Berlin that they were searching for such a system for 4 years and they didn't find any. So our system is the first which works enough for them. There can be exhibits in museums, much more lifelike. We can enhance video conferencing. And again, now it's not Star Trek, but Star Wars. If you remember, Council of the Jedi, they sitting around in a big room, and some of them in reality and some of them as holograms, and still talking to each other like being actually there. That's what we like to do. And in the future, there will be party, personalized auditory reality. And the idea is that there, all these sensors will be there, so I can adapt to the room acoustics on the fly. I walk in a room, it takes a few seconds, and the system knows how the room sounds, and it knows the audio sources around it. So we can have people I want to speak to, foreground audio objects. I want to hear them. I want to reduce the overall loudness. So that's background audio object. I have some people yelling and I don't want to listen to them. So I can put down the amplitude for them with just a little bit. Or I can do the same in other environments like theaters, airplanes, and so on. I always can have something around me, which is like a auditory scene, but it's working with a lot of artificial intelligence algorithms because it really adapts to the environment and it lets me listen to the world around me like something, listen like glasses for people who need glasses. Normally, I don't even realize I have them on. In fact, it happened to me that I was searching for them and oh, they are on my nose. And the same should happen for headphones. Perfect, transparent listening, and then you can enhance and change what you want to listen to. So for that, we need very good externalization. We need fast adaptation to the room, very difficult. We need auditory scene analysis in real time. The question is, can we really do that in the future fast enough? And for sound separation, the same thing is there are some hard problems which we still need to solve. Of course, we need a nice user interface, but if we get all this, we can have party headphones, and all who have worked on this, I remember from time to time we are somewhere and said, oh, now we would need our party headphones. Too bad we don't have them yet. So let me conclude. While it will take years to implement all the ideas, including party, new ideas for binaural reproduction of sound can be demonstrated today. There's very big progress on the rendering side. Takes the acoustics of the room into consideration. We can avoid measuring the personal head-related transfer functions. So no scanning or no photos of your ears necessary. Advanced rendering works with basically all kinds of input, from broadcast, channel-based, object-based, formats like MPEG-H, Dolby Atmos, and again, we need software for decoding, but otherwise, yes, we can do that. But we need headphones with the right sensors, including fast and reliable head tracking. We can't do that with just listening over YouTube and having stereo headphones. That won't work ever. But after more than 40 years of research, we finally can demonstrate fully plausible binaural reproduction via headphones. And that was my talk, and I think I was in time, so I'm looking forward for the discussion. Thank you very much.